Hello everyone, and welcome to this video, the third in this three-part series, third and final, and it's on the Stokes theorem on curved manifolds using differential forms. All right, so let's make a start. Okay, so in the last video we found that the integral of the omega, the exterior derivative of this form omega over the manifold, was equal to all of this. Remember how we came out about this? We went through a lengthy process developing the divergence here, covariant derivative, this vector, and we found that it had this form here as well. And we showed that the left-hand side here was equal to the right-hand side with some examples, and that this yields between the top line here and everything else we did, this yields the divergence theorem on a curved manifold. Okay, so that was the goal we were looking at there. We looked at some examples and one involving the Schwarzschild space-time metric, and I might just hide that now. Okay, so here was the Schwarzschild space-time metric, and we're going to now have a look at in coordinates CT r theta phi, and f of r is this term here, so that we had the determinant became this. Okay, and then the square root of the absolute value of the determinant was this object here, which appears in the volume element in Schwarzschild space-time, or just in general, you have the square root of the absolute value of the metric on a curved manifold as being the volume element, part of the volume form, or whatever dimension you're in. Now, let's say we're given this vector field x mu, and it's just going to have one component that's just in the r direction. And we'll label it just for no particular reason, just surely for the sake of an example, to keep things simple, we'll have the r component will just be the variable r. All right, so we found that the covariant derivative of this vector here, using this formula here, well, in this particular case gave us this, because remember, square root term here is this. Okay, when we did that, carried out that operation, we had 1 on r squared partial over partial r of r cubed. Okay, the sign terms here cancelled out. They don't take part in the derivative. The derivative is only with respect to the variable r. So we get this object here. So we get 3r squared in here times 1 on r squared, which just gives us 3. That gives a very simple example. Very simple example. Nothing terribly complex, just to make our point. All right, so next one over here. Next, we integrate the volume form. So the integral over m is the covariant derivative of the vector here times the volume form. And when we integrate that into each of its components, we have, here's the volume element, dv, that object there. And we're integrating, if you remember from the example, we had our limits and so on, which I'm not restating here, but phi from 0 to 2 pi, theta from 0 to theta 0. And we had between r0 and r1. Okay, we had the hypersurface bounded by these. Time component, when we conduct all that, separate those out, multiplying them together, it ends up, we come out with this object here. So that was on the left-hand side. Okay, and then next we wanted to look at the right-hand side. Remember, there was the integral of omega over the hypersurface form, the induced surface. So next we created a one form from xr equals r in the following way. So alpha, this will be our one form, was x lower r. Notice the subscript here is r, right, is in the covariant position before it was in the upper contravariant position. And so we have a form of this form, x subscript r, x covariant r dxr. And we can get that lower term using the metric to lower this contravariant component. Here like that, that equals that times the xr. Well, GRR is 1 on f of r, if you remember for the metric. XR is just r times that. And from which, now if we're going to integrate omega over the hypersurface, then we're going to need the Hodge dual. Now, from which we then produce the 3 form, which is the Hodge dual of this object. Okay, so omega will be that, but this time times the Hodge dual of dxr. Okay, and as we're in four-dimensional space, this will be a three form over here. Next bit, so omega is this object here, okay, which is that, and the Hodge dual of dr, of the one form dr in a four-dimensional space, is a three-dimensional, is a three form. That's this object here. So putting that in, notice that this inverse metric term cancels with a metric term here. We left the xr times what's left over. Now, epsilon rt theta phi we found in the last video was -1. Because we're going to be integrating, we're looking for the volume form that's positively oriented. So we need for the volume element to integrate, we need the positive element. And also remember this one on n-1 factor, because remember if n is 4, then 4 minus 1 is 3, 3 factorial is 6. So we know it's 1 over 6 factor. But that's just because we only wanted, when we use this formula, we only want a single instant of this. But what we want in general is the form, the general name of the general shape of the form itself. We don't want any particular instance of it, of which there are 6 in this 4 dimensions. So we arrived at omega is this, okay, and then we're going to integrate that over the hypersurface, over the surface of the manifold here. That's the induced surface, the induced hypersurface, and we're going to have this here and evaluate, if you remember, R1 and R0. Well, if you notice here, the integral is over phi, theta, and t, not over r. And we only evaluate r at the hypersurfaces themselves. And one was R0 and the other one was R1. So they're the induced hypersurfaces. And so that becomes just R1 cubed minus R0 cubed. This integral here gave us c times t1 minus t0 in parentheses. This sine theta gave us evaluated the terminals, 1 minus cos theta 0, and then phi gave us 2 pi. Now this one, okay, so this is the right-hand side, and we've seen that that's equal to the left-hand side. All right. So these results verify Stokes' theorem on the curved manifold of the Schwarzschild space-time. So the left-hand side here equals the right-hand side. Now what we're going to do is, I just want to focus on the vector part. So it's a little bit of going off on a tangent here. I just want to focus on the vector operations because it's part of this channel as well. So let's just have another look at the right-hand side of this equation. So the induced three-metric gamma ij on the r equals constant hypersurface is just the restriction of Schwarzschild metric to the ct theta phi coordinates. And so the induced metric is this, okay, the t, theta, and phi, from which we get this, okay, the square root of the absolute value of the induced metric here gives us this. And then and if you remember the right-hand side here, I just want to have a look at some vector operations just to round out this story. So we have the integral of omega over the boundary is the integral of this vector object here. ds is the area surface element, n is the vector normal to the surface, if you remember, but we had lowered the mu here, the index mu, and we have our vector here, one up, one down, because we're summing them. All right, so we are considering the hypersurface defined by r equals constant. This is a 3D surface embedded in the 4D space-time. A vector normal to this hypersurface, so we're just looking at a bit of vector operations here just to round out the story. So we get n is nr dr, because we just want a vector normal to the surface. We want it just in the purely radial direction only. And so we have this object here, which has component 0, n, contravariant r, theta 0, 0, sorry. And we know that for a unit vector, it must be normalized to 1. So n dot n is this object here, equals 1, implies that times that is, well, GRR, the metric term is 1 on f of r, if you remember. And then this object squared equals 1, from which we get nr squared just is f equal to f of r, and that implies that nr, the component here, is the square root of this object. We'll take positive because we're on outward oriented normal for the purpose of integration. which gives us n mu is this object here. All right, so there's our vector normal to the surface. All right, now we can find the covector or covariant form using the metric to lower that index. And what we get is this times that, so we get 1 on the square root of f of r, and that gives us an n lower mu, n covariant mu is this object here. All right. So really it's just an example working vector, but since this is part of the general relativity channel, I'll include it as well. All right. Now, using x mu as that's our original vector here, along with ds is the square root of this object here, which I won't go into here, but there's the volume element for the induced metric on the induced surface, on the hypersurface, as the induced volume element on the boundary of M. So coming back now here to the right-hand side of Stokes' theorem, we have this object here, and we put that in now. Remember, we're going to evaluate on the boundaries, sigma r1, sigma r0. And so we have to evaluate all of this. Well, x mu, as we found, is r, n mu. Well, what we need is xr here, nr here, so we get r times 1 on the square root of f of r. Then the induced metric here, the square root of that, the absolute value of the square root of the metric is this object here, square root of f of r times r squared times sine theta. Then we have d phi, d theta, c dt. Okay, let's work through this integral here. And we have that evaluated at the boundary here. So that gives us the r1 cubed minus r0 cubed. And 0 to 2 pi d phi, integrating that at these terminals here will give us 2 pi. Integrating sine theta d theta from 0 to theta 0 will give us this object here. And then c dt integrated gives us c times t1 minus t0 for those terminals. And that just shows that this, which is this here, the right-hand side, is equal to the left-hand side. So it works yet again, whether we're working with forms or we're working with vectors, both give us the same result. All right, so let's move on. So finally now the conclusion is that, can we turn that now? So we have that Stokes' theorem in differential geometry is a generalization of classical vector calculus results to arbitrary curved manifolds. Using differential forms, it provides a coordinate-independent way of understanding integration and boundary interactions in curved surfaces. Doesn't depend on the coordinates. The theorem is crucial in general relativity, differential topology, and gauge theories. All right, so that concludes part 3 of this series. Thank you very much for watching. Please push the like button and subscribe if you will. Thank you very much again for watching. Take care of yourselves wherever you are. I hope you're having a good day or evening or whatever it is where in your time zone. And I look forward to seeing you in the next video. Thanks again for watching, and I'll see you next time. All right, bye.